So let's use Duhamel's principle. We're going to concentrate on a few simple cases, not where we really get a lot of new power from it, but just want to confirm that it's working like we would expect where we have some intuition. And then maybe I might do an extra handout and video or some videos about a little more complicated cases where this would really be a novel way to solve something, a really useful way to solve something. So we've got my prime, double prime, plus m omega squared y equals f. Undamped, just for simplicity, makes the details a lot easier. Forced harmonic oscillator, and y, it starts out at 0. And we're going to see that this kind of thing, worrying about boundary conditions, which we have to do, or I guess initial conditions, which we have to do to make the solution unique, does bring in the issue of where supports are in a way that's much less technical than it would have been just sort of proving what we were doing with the rest of the handout, and actually give some meaning to it. So I'm going to go ahead and take advantage of that, even though we're not focusing on the support issues too much. Okay, so fancy way to say this is we've got a linear operator md squared plus m omega squared, and we're studying Ly equals f, to put it in that general context. Okay, so suppose we know that U is the special solution that satisfies LU equals delta. Okay, and we know what that is. We've done that before. That was U, that was a function. There's no need in this setup for it to be a function. It can be a distribution. Although in the next handout we'll talk about the kind of boundary and when you really want things to be functions. U of t is, to get the coefficients right, 1 over m omega, I believe, unit step function h of t times sine omega t. Okay, it's just a sine wave with the right frequency that turns on at 0, and then this makes sure that when it turns on, m times the second derivative gives you that delta. This guy doesn't do really anything there because it's just multiplication by a number. It can't turn this continuous function into a delta function. It's really just that that's giving the delta. But we've done that before. Okay, so, and then the claim is that the solution here is just y equals that guy convolved with f. Very slick. Okay, so that's the sort of simplest example. That's our leading example of this. So let's look at the support issues a little bit. Okay, so let's suppose that the forcing turns on sometime at A or after, and then ends at B. Because remember, we've only really proved this where this was a test function, and that's not really necessary at all, but that's what we've done. So say it's compactly supported within the interval A to B. So now instead of that delta forcing, we've got some forcing that's like turns on and then ends. And I'm not assuming A is positive necessarily. It could have turned on before we started our stopwatch. Okay, the claim is that the support of y, this convolution, is a subset of A, but it could go off to infinity and probably will. Okay, so in particular, one thing I haven't checked about this is that it actually satisfies these initial conditions. The proof of Duhamel's was just about how distributions, derivatives, and convolutions interact, and it wasn't talking about this. Okay, but this certainly says, if it's supported from A going to the right, that certainly says that y of minus infinity and all of its derivatives are 0. And remember, these are not really evaluating at minus infinity. They're limits as x goes to minus infinity of these quantities. Okay, but they're certainly going to be 0. All right, so we want to prove that claim. And it's just a special case of a general result we're going to prove eventually about supports of convolutions, which is helpful. Okay, so y of t, just to write it out explicitly, the 1 over m omega is not essential. Okay. Here's the convolution. So we plug in t minus tau, there's a minus sign there, into the u function. Let's just get that out of there, even though it's useful. I don't think I have space for it. Okay. Let's just leave u separate here if we need it. Okay, now this guy is, this is supported from a to b, so this isn't really an improper integral, which is a good thing for kind of technical proof results, of course. And I'm just going to rewrite the whole thing, I guess. Okay, we still need to know the details of f of tau if we want the answer, but the key is that it's an integral from a to b. Now let's think about this h function, okay? If t is less than a, then you're going to take a number less than a and subtract a number that's a or bigger, and of course that's going to kill this unit step function. Then this vanishes, the integrand vanishes, because there's going to be no taus in this interval that actually make it non-zero, and therefore y of t equals 0. Okay, so y vanishes for t less than a, and that says the support of y is in a infinity. Okay, so physically speaking, I ask in the PDF, what does this have to do with causality? So now I need the picture again. So actually, let's assume the forcing actually did start in the past, just to make it clear that's okay. There's A, there's B. And what we're doing, of course, is we can think of that as using that as a weighting and adding in a whole bunch of translated copies of this oscillation. So there's going to be a translated copy that starts here, and it's going to be really small, and then a translated copy that starts here, a translated copy that starts here, a translated copy that starts here. And none of those guys are going to do anything over here. And physically, that's, of course, very, very reasonable. This spring is just sitting there, and we hit it with a forcing. We shouldn't see an effect before the cause. Okay, so F is the cause, and Y is the effect. And we're saying that with this particular solution, then we get causality the way we expect it. That does work out. But what I want to point out is that was a little special. Okay, there are other solutions to LU equals delta. Okay. Oh yeah, and one of the other things I ask in 11a is it crucial that the support of F was bounded on the left or on the right? Well, F had bounded support like this. Let's imagine that we could extend that proof a little bit. Oh yeah, F was red, I guess. The forcing like this. Suppose the forcing had gone on forever. It had been doing that forever, and then maybe kind of tailed out after a while. If that's F, then we've got a major problem here. Then we're trying to convolve this function, and the integral, remember it reduced down to the integral from a to b of all this stuff, and sorry I erased it, that would be a minus infinity. That would liable to be, that's not very good English. It would quite likely be an infinite, a divergent improper integral. So mathematically, that's bad. And another way to see that's bad physically is if I've been forcing this from time immemorial, then I'm going to have effects from that are coming from minus 1,000,000 years, minus 1,000 years, minus 100 years. They're all going to add up to probably an infinite actual, ooh, what was my, blue is the color for the actual function, right? It's going to have an infinite effect in the present, okay? And that's recorded mathematically by a divergent integral, okay? So it wasn't really crucial that F have compact support, but this kind of picture is certainly out. And so certainly this kind of picture for F, if it just never started, it was always going on, never stops, that's bad. But it's really mostly about this that's bad. Now this is what we need. So this is kind of getting towards a little bit more towards when we do support conditions carefully. That's what we really need for F, is it started at some time in the past and then goes on. Maybe we could get away with this thing decays very, very quickly in the past, and there was a tiny effect from way, way back, but that's kind of weird. That's not a very physical situation. So it's much more reasonable that with the spring was sitting there, sometime in the past the forcing started, and the effect of that comes after the cause. Okay, so just to get that a little bit more clear that this is a real issue, that's what B is about. Let's look at V of t is just u of minus t. In other words, it's 1 over m omega h of minus t sine of omega times minus t, but it's going to be easier to write that with a minus on the outside. Okay, and what is that? All I'm doing is flipping it across the axis. And the claim is that still satisfies. Yeah, sorry, I should have drawn that right to left. There we go. Okay. That still satisfies LV equals delta. I'll leave it to the PDF to do the details of that. It's a fairly standard variation on how we were proving that before. Probably the cleverest trick being shift it so that we can kind of shift out the singularity in V prime, because V prime is the real tricky thing to take the derivative of. That looks like this. It's got a jump. And you can't take an ordinary derivative of that, and we know there's going to be a delta there, but, ooh, actually, it's minus. We have to be careful about that kind of thing. Okay. So, the point is that physically, this is a solution where the spring has always been, from infinitely long in the past, it's been oscillating, and then what happens, how does the delta come in? The role of the delta is to stop it oscillating, and then it never does anything anymore. So it's quite opposite from the other fundamental solution. And of course, this thing does not satisfy v of it does satisfy v of infinity, and v prime of infinity is 0, but not minus infinity. It's definitely doing interesting stuff at minus infinity. Okay. And so what would happen if we use this to convolve with, if I look at y equals v star f? What we proved last time is that's still going to have Ly equals f. That's fine, but it's not going to be the solution we really want in most cases, because what's going to happen? The support of that guy, it's not hard to see that the story gets reversed, and you can look in the PDF for the details. That is going to be contained in minus infinity to b. Okay, great. Well, that means that the support of the effect doesn't go after the cause, but it can go before it for an arbitrary length of time. That's weird. Okay, so here y, which is the effect, you can see that, right? Yeah, the effect is before the f, which is the cause. Not so good. Okay, now there's situations in physics where you actually do play fast and loose with this, or you really get pretty interesting about what's called advanced and retarded solutions to differential equations, like propagation of light and everything. It has to do with all kinds of stuff like time reversal and Feynman diagrams, but it's definitely not something we should do and think, oh, that's exactly what we meant to do. So the point here is that things like boundary initial conditions and questions about support can have deep meaning, and can really pick out which solution. They can help pick out, and sometimes they're crucial for picking out, which solution of Lu equals delta do I want? Because just knowing this, and this is something you're told from the very start of differential equations, and it's not false now that we're just doing distributions, just giving me a differential equation doesn't make a unique solution. You need some other condition. And one actual way to say that is not so much about values or initial conditions or boundaries. It can be just about a support condition, providing that extra information. Okay, so let's continue, since make it a little longer. Actually, no. I'll do the next problem or two in another video.